In this video, we're gonna look at some other transformations of exponential functions. So far, we know the parent function that looks like y equals to b to the x. B is our base. Sometimes we have number a multiplied to b to the x. So if the absolute value of this number is greater than 1, then the graph stretches vertically. If the absolute value of a is between 0 and 1, it shrinks vertically. In other words, we use word compression. Sometimes the a number is negative. That means the graph is reflected across the x-axis. In other words, the graph flips. So we're going to add on two more translations. These are horizontal translation by h and vertical translation by k. So if you have x minus h instead of x, then the graph has been moved h units to the right. If you have k added at the very end, then the graph shifts k units up. If you have this kind of form, a times b to the x minus h plus k, that means it has three transformations going on. It has vertical stretch or shrink depending on the absolute value of a. Also, sometimes if a is negative, then it means it has a reflection across the x-axis. It has x minus h, meaning that the graph moves forward to the right. If you have k, up k units. So let's go through this example problem, see how that really makes sense in a real example. How does this graph compare to the graph of the parent function? So when we're talking about parent function, it's always the form of y equals to b to the x. That means we don't really need this a number, we only need b and the x. In our case, the parent function of this function would be y equals to 3 to the x. So we're gonna complete the table and then plot these points and see how they actually how this is different from the parent function. So if I plug in negative 2 to the x, I'll get 1 over 9. Plug in negative 1, I'll get 1 over 3. Plug in 0, I'll get 1. Plug in 1, I'll get 3. Plug in 2, I'll get 9. So negative 2 comma 1 over 9. Negative 1, 1 over 3. 0 comma 1, 1 comma 3, 2 comma 9. So this graph has the characteristics of a parent function, which means it always passes through 0 comma 1. 0 comma 1. It also passes through 1 comma b, which means our b is 3, so that means it passes through 1 comma 3. So now we're gonna multiply these numbers by negative 1 over 3 to get the y values of this function. So if I do that, I will get 1 over 9 times negative 1/3 is negative 1 over 27. This will give us negative 1 over 9. This will give us negative 1/3, negative 1, negative 3. So I just multiply each number by negative 1 over 3. And I'm going to plot these points. So negative 2, comma, negative 1 over 27, which is really close to the x-axis, but not really touching the x-axis. Negative 1 comma negative 1 over 9, 0 comma negative 1/3, 1 comma negative 1, 2 comma negative 3. And if I connect these points, I'll get a nice curve, the red curve. If I compare the red graph to the blue graph, we see there are two transformations going on. First, the blue graph has been shrinked vertically. See how this the distance between this point to that line, which is 3 units, has been shrinked to just 1 unit from here to here. So because of this number, 1 over 3 is the absolute value of 1 over 3 is less than 1. That's why we have the vertical compression by factor of 1 over 3. That means each point has been multiplied by 1/3. Also, we have another thing going on because our a number is negative number. The graph has been flipped across the x-axis. So in fancy math vocabulary, we say reflection across x-axis. So it's like the reflection. This is like well, anyway. If you look at the domain and range, if you look at the domain of blue and the red function, they are both all real numbers. So these two transformations did not really affect the domain. So domain is unchanged. If you look at the range, however, the range of the blue function was y is greater than 0. Now you look at the red one, it's below the x-axis, which means y should be less than 0. Because we flip the graph, the range has been changed. If you look at the asymptote, both of these two graphs has the same asymptote, which is the x-axis. So it's not changing, unchanged. Okay, let's look at two little bit maybe more complicated example. So how does the graph of each function compare to the graph of parent function? So now we know the parent function is always the y equals to b to the x. So our parent function of this function will be y equals to 2 to the x power. Now just by looking at that, we know that because we have x minus 4 instead of x, this x, h, the 4 represents the horizontal shift. So that means we have horizontal shift or translation, and we're gonna go right 4. So if I plot the points of our parent function, it's gonna pass 0, 1, 1, 2, 2, 4, 3, 8. And it's going to have asymptote of the x-axis. Now we're going to move every point right 4 units. So this point will become here, this will move up to here, and so on. So we're going to have this red graph. Basically, we move the whole graph 4 units to the right. If you compare these two graphs, you will see that domain of these two graphs are both all real number, so domain has been unchanged. If you look at the range, but they have both y values greater than 0, which means they are both above the x-axis. So range hasn't been changed. If you look at the asymptote, they have same asymptote, so asymptote is also not changed. Let's look at this function. A little more complicated. So we start with a parent function which looks like y equals to b to the x. In our case, it will be y equals to b, which is the base, to the x. So for now, we are not really thinking about 20 and 10. We know just by looking at that though, we have 20, which is our a. So and then the absolute value of 20 is larger than 1, so it's gonna go vertical stretch, not shrink. So we're gonna have some kind of vertical stretch by factor of 20. That's one transformation. Also, if you look at the 10 added at the very end, that's the number k, so we know it's gonna be vertical shift, or you can say vertical translation by 10. So that means the whole graph is going to move up by 10. So now let's plot some points to graph our parent function. So we know it's going to pass 0, 1. So 0, 1 right here. Let me graph in black. And it's going to pass, if I plug in 1 here, it's going to pass a half. So 1, half around here. And it's going to have the asymptote of the x-axis. So that's our parent function graph. From here, we're going to apply this number 20. Let me do that in blue. So this 20 means the vertical stretch by the factor of 20. That means each point will be stretched 20 times. So 1 will become 20, and this was 1 comma half. So half becomes, half times 20 is 10. And it's gonna look something like this. Notice that we still have the same asymptote. It's just that the black graph has been stretched 20 units. Finally, we have this 10 added, which means the vertical shift by 10. That means the whole graph is going to move up 10 units. So 20 will become 30, and 10 will become 20. And notice that the blue graph has the asymptote of the x-axis. This asymptote is going to move up 10 units as well. So if I move that up, this line will be our new asymptote. So our new graph will look something like that. So if you look at the red graph and then compare that with our parent function, which is the black graph, our domain hasn't been changed because it's always the all real number. So this is unchanged. Our range is somewhat different because the black graph had a range of y is greater than 0. Now the red graph has a range of y is greater than 10 because the red graph is always above this line. So range has been changed to this, and as I mentioned, asymptote has been changed. Previously it was x-axis, now it's this line, which is y equals to 10.